today I speak to somebody who looks at antiprotons. I also speak to him about how India is participating in a mega research facility where India is a part owner. The facility is not in India, the facility is in Germany. I'm speaking to Dr. Paolo Giubellino. I hope I got the name right, the second name.
Absolutely.
But I will continue calling you Dr. Paolo. Welcome to the program. And in COVID times, the Indian way of greeting, which is namaskar, is the way forward. Dr. Paolo, tell me a little bit about this fair. Indians know fairs only as a mela or as some place where people go have fun. What is this facility for antiproton and ion research?
So FAIR, as the name says, is a facility for antiproton and ion research. It's an international research center, which is currently under construction on German soil, but by a group of countries, some European, but also Russia, India. And when I say it's under construction by a group of countries, means that, yes, as you just mentioned, they own this facility, but they also build it. We will probably come to it in some time. It's not that from India we get a check. We get the construction in Indian laboratories and in Indian industry of components, and then are put together with the components built in many other different countries to finally have this facility. Why do we do it? We have a great ambition that is that's our motto in some sense, to bring the universe in the laboratory. That's not just a motto, it is really a description of what we do. There are a series of fundamental processes in the history of the universe which have determined what we are now, the universe around us. And that we can understand, of course, through measurements about the universe, but that always is very indirect. What we can also do, and that's what our job is to reproduce these processes in the laboratory so that we can study them in detail and really understand them. For this, you need accelerators, you need detectors that then study what happens in the events, and you need then the brains and the computers which analyze the data which come out. So it's a whole process which starts in the brains of people which have the ideas about the experiments and the measurements, the construction through the development of new technologies of all of this equipment, and then finally taking the data and looking at them.
While you and I both are made of stardust.
Absolutely.
Why do we need to understand what is happening in the universe at a scale where you are looking at, which was very early in the universe? Why don't we look forward?
Oh, we look both forwards and backwards. And first of all, look, we are human beings. Human beings need deep insight to know what we are, what it's all about. It's, if in some sense, it's a fundamental characteristic of humanity, that we are driven by curiosity, which, by the way, then allows us to build new technologies, to find a cure for diseases and all of these things. But that all stems ultimately from our drive for knowledge, for simply knowing what happens. Let me give you a small example, because we have very many experiments, but a simple one. It's by no means the most important, but it's just to give an idea of the type of things we do. we are made of carbon and oxygen. And we know in general terms that carbon and oxygen are produced in the late phases of the life of stars. That's when they get produced. But how much carbon, how much oxygen, how the building blocks of life, how are they made? And already almost 40 years ago, when Fowler got the Nobel Prize, in his lecture at the Nobel Prize, he said, the most important and fascinating thing to measure is how in the reactions in the stars we produce carbon and oxygen. Well, you might know that 40 years later, this has not yet been measured. It's a very difficult measurement, and that is something that we will do at FAIR.
Mm-hmm.
And you do it in the laboratory in controlled conditions so that you can actually understand what's going on. This is just one example, but there's many, many, many from where all the gold and other early elements come from. We are all curious about where gold and platinum come from. Well, they come from a very exotic process, which is the merger of neutron stars, which is certainly not something which we know in everyday life or that it is easy to observe, but we will be producing that in the laboratory at FAIR.
How will you be making the universe in Germany on ground?
What we do is that we accelerate nuclei, then we make them collide. When you collide nuclei, you compress and heat matter so that you mimic, reproduce on a small scale. I use the word mimic because it's not exactly the same thing. It's analogous. You produce strongly interacting matter, nuclear matter at very high density and a very high temperature. And those are the conditions which are prevalent, for example, inside the neutron star. But we also produce matter in extreme conditions, which is important for the other understanding. Let me give you another example. You have planets. We send nice space vessels that take pictures of the planets, but what's inside planets? What's inside even our planet, under our feet? Well, it's very poorly known because these are extremely high density matter conditions that, again, we will be producing in the laboratory so that we can reproduce in the laboratory what's the interior conditions in the interior of Jupiter, in the interior of Saturn, in the interior of the Earth. So it's fascinating the fact that a bit all of these pieces of the puzzle that we need to put together to understand the structure of the universe as we have it around us are addressed by different pieces of our facility, which is now under construction. And so it is not an experiment, it is an array of many different experiments that address different points. It's a bit like when you say we build a space station. It is not to make an experiment, it's to create the conditions to do many different experiments. So our ambition is to be a bit like a space station on Earth that provides a number of different opportunities for people to measure different things. And of course, for that, you need brains. And that is a fundamental point. Science is done by a combination of creating the conditions, but then some brain, some person who has the creativity and the know-how has to turn that into discoveries. And then you really need a lot we have more than 3,000 scientists involved. And actually many of them are in India. It's one of the countries which has, imagine that's 27 scientific institutions in India which are involved in this project. And this means...
Let's dwell a little bit on the India involvement. What is India's involvement at this facility for antiproton and ion research in Germany?
Well, I would say it was India, one of the centers already since a long time. It has been since a long time, one of the centers for nuclear physics in the world. This has been one of the areas in which Indian science has been leading, and that was also in my previous history at CERN was extremely important. Before coming to FAIR, I was leading one of the experiments at CERN, and again, the presence of Indian scientists was essential. Therefore, because of that, a number of leading Indian scientists were at the origin of the creation of this facility. This facility is being created because of the ideas of a group of scientists, of which several of the leading figures were Indians. People like Professor Singha, people like Professor Saraja. They were not just somehow participating, they were some of the initiators. I mean, FAIR looks the way it looks because some Indian minds defined it in this way, together with Germans, Russians, British, French, Polish, and whatever. But this was really at the moment in which this was conceived. It was an important process because if you look on paper, these big accelerator laboratories look very much alike. But if you then look well inside, they are very different, very, very different. The way you, let me give you a simple example, if I may take a bit more of your time on this point. Let's compare CERN, which is my previous institution.
The Large Hadron Collider.
Exactly. Now, when we do experiments, what are we doing in the end? We are looking at things. So let's do an experiment like the ones we do. I have a cup, which is the object of study. I have a source of particles, which is the light, which I have on my ceiling. The photons, which are particles, hit my cup, and they interact with it, and then they reach my detector. The detector is my eye. And then the information is transported to the computer center in here, and we process it. And I understand how the cup looks like. Then I want to proceed with science. And then there are two different directions in which I can go. I could go to have higher energy projectiles. So instead of the photons from the light at the ceiling, I will take X-rays, for example. And then I would do an X-ray of this. And then further and further, higher and higher energies, looking at smaller and smaller details. That's what CERN does. That's their job. What we do here is the opposite direction. Instead, I want to look globally with more detail, but at the global features of my cup. Then I turn on the light. Before it was a bit dark, the room, and I get the room brighter and brighter so that I can see more and more the complexity of the object I'm seeing. So you see that, and that is fair. Higher and higher, what we call luminosity of the accelerators, which means more and more particles in them. And that is the basis, for example, of the fact that the Indian scientists, which were specifically leading the studies of high density nuclear matter, were interested in going both ways at CERN at the highest energies in ALICE, and here at the higher densities, at the higher intensities with the CBM experiment. Because the two information provide us two very complementary views of the way nuclear matter behaves. And it is a bit like saying, well, you study water. You are never going to learn about ice by studying vapor of water, or vice versa. You are not going to learn about the way the clouds form by studying ice. You need two different complementary avenues, and that's what we do. In some sense, you could say CERN is studying vapor, FAIR is studying ice. And they are both very complementary ingredients to our understanding of the many facets of water.
Could you not have done the same experiment at CERN? Why do we need to invest 3,000 million euros in FAIR?
Because these are as I said, two completely different machines. One which is the one which gives you the highest energies. The other one is the one which gives you the highest intensities. The two is, why would you need a radio telescope and a visual telescope? Because they give you two very different informations. It's not that making a bigger optical telescope replaces having a radio telescope. They are two different pieces of information that complement each other in understanding. So there would have been no way to do that at CERN. And you can see that the very same scientists push the two ideas because they want to get the full picture and they want to have the complementary information. Neither would suffice.
When do you hope to complete the facility, which is under construction?
The current goal is 2025. There might be a bit of uncertainty because of the COVID situation. This might introduce a little bit of delay, but, and this is an important but, we start using on the way whatever is already ready. It's not that it's a complex facility. It's not that one day it's all in operation. You start whatever component you have available, you start using it. And therefore, there are components which are already being used now. So in some sense, your correct question was exactly as you formulated it, when it will be completed. Because if you would have asked me, when would you start using it? And I said, well, we have started actually last year. So it's a process in which you start with small parts and then progressively you reach the full use of the facilities. But there are experiments which are ongoing. Actually, in this very, very moment, there are experiments which are taking data. Of course, when the full facility will be available, it will be a lot more interesting. But today, there's science coming out. Indeed, there are considerable numbers of our Indian colleagues which are on campus all the time.
How many Indians
by the way,
are there?
The number is very considerable. I have to look up the exact number, but it's from 27 institutions. Okay. Let me clarify. This is a host institution, it's called. So how it works is the following. You have people which work here permanently, and at the moment I think it's about 30 from India, but they are the users. So those who, while being professors or students in an Indian institution, actually use the facility here. For example, there's 50 PhD students in India at this moment who are doing their PhD thesis on FAIR. There are of the order of 60 or 70 scientists in all of these institutions which are working on FAIR. These are not here all the time. They come for some part of their time. So the answer is three different numbers. A number of people who are actually here, part of the staff, people like Pradeep Ghosh, for example, which is one of my direct collaborators. And those are about 30. Those who are in India for their own institutions, and those who do their studies through our institution. So you have both you have different numbers, and I think it's important to see both, because our target, our mission is to provide opportunities for people who continue to work in their own institutions. We are not a brain drain vehicle. It's not that we want people to come and move here and work here. That's not our way of working. Our way of working is that one is a professor in Chandigarh and uses the facility for his or her research, and the students of this professor will use the data and the facility to develop their skills and to do their science. So this is the model.
What is your experience with the Indian government and the Indian scientists? Has India been providing you the necessary resources on time?
Definitely. I mean, there is always some time issues in bureaucracy, but you know, I'm Italian and I know that very well. I have plenty of experience with bureaucracy. I think that overall we have been finding in the Indian government an extremely intelligent and cooperative partner. With Indian scientists, I think it's difficult to say from what I was saying before. The facility exists because of the way Indian scientists have conceived it. So their role is not just that they are, is not saying, I say, well, they are participating. Well, we exist because of them. So they are at the core of what we do. And I only hope that now that there are data being taken and so on, that even more of the Indian students in particular will use this facility for their research. Because something that I did not mention before, because of our primary goal, which is this understanding of the universe, we have facilities which have a very broad range of applications. In particular, for example, this laboratory has been the laboratory pioneering cancer treatment with nuclear beams, which has done, now is finding direct clinical applications. But also we are involved in the development of vaccines right now. We are involved in development of, for example, the future nuclear clocks. One might think, why do we need anything more precise than atomic clocks? Atomic clocks are already fantastically precise. Why do you want to go more precise than that? Well, think about it. The main application of precision in time and measurement is your GPS. That is the main application, actually, of atomic clocks. The precision of your GPS depends on that. Now, imagine an airplane who would want to land using the GPS. Would you feel safe? Think a moment of when you look at your GPS on your phone. What is the precision? A few meters. Do you want to land with a plane which is a precision of a few meters? Not really. You would prefer to have a few centimeters when you are approaching the floor, the sun.
Dr. Paolo,
for that, you need 100 times more precise clock.
I am also told that as more and more the world is becoming digital, in the era of cyber security and cyber crime, precision time is very critical. What are your views on that?
It's of course. So you have a number of applications. As soon as you vent the idea that maybe someone could produce a clock which is 100 times more precise, you immediately find a range of applications. Exactly, you mentioned cybersecurity. self-driving cars, and so on and so forth. There is a number of situations in which highly precise time measurement would make a world of difference. And for the moment, the future that we see are nuclear clocks, and we are participating in developing that. So you see that there is a number of everyday life applications that are, by the way, all this relies on a lot of number crunching and of working on huge data samples. This laboratory for FAIR has developed at the moment the most energy efficient computer center, which is called the Green Cube, Green IT Cube, which got a prize this year and actually in Germany, is the most energy efficient large system. There are small systems which are as energy efficient, but other large systems, because in the end, the money you spend to cool your computers becomes comparable to the overall cost of the computer center. Mm-hmm. So this is one of the things in which frontier developments have been made, and there's many, many others. So
essentially, now towards the end, you're largely doing fundamental science and basic science research, correct, sir?
That is our driver, our mission. Yes.
And then what are you mentioned about cancer research and cancer therapy probably. And you mentioned about atomic clocks. Are there any other areas where you think this heavy ion research could help? Or it would be just the finding of your former Large Hadron Collider found God particle. Will you look for the God mother particle?
No. There is a lot of technologies which are developed in this in the process of this fundamental science that are of extreme importance. I just give you a simple example, but because again they are very numerous. We have developed here and pioneered this way of treating cancers with nuclear beams. Why is that particularly important? Because it spares the healthy tissue around the cancer. So some cancers are surrounded by very precious tissues. They are in the brain or in the spinal cord or in the eye, where it is extremely important to have a very precise tool which can destroy the cancer cells in a well-defined place. But our scientists then thought, well, so we have a tool which allows us to destroy cells inside the body without cutting it. Like in a science fiction movie, you can actually have a scalpel which goes cut inside without opening. Could we use it, for example, for heart surgery? The answer is yes. It has been tried last year in the laboratory here, and it works. You can actually intervene for an ablation in the heart without opening the patient. With it, of course, it's fascinating. There are
and this was done at FAIR?
It was done in this so-called FAIR phase 0. I mean, these activities which we have currently. Yes. Well, with pigs at the moment. We are not doing it on humans yet.
Everything starts somewhere. Well,
you don't want to experiment on humans right away.
I quite agree, and pigs are very.
But let me mention another field which I think is very relevant. We all now are admiring the trip to Mars of the rover, and people think, well, there will be humans soon. For trips of humans, it is not so negligible the fact that you have big dangers due to radiation in space. And that is one of the drivers of our common research with the European Space Agency, and I hope with other space agencies in the future, because our beams are the perfect tool to understand what happens to a human body while traveling on long trips in space. I was recently at a presentation by NASA who also said, well, we will also come to FAIR for this because that is where the perfect conditions can be reproduced. And we have to understand how to mitigate the effects of radiation, because otherwise we will have our poor astronauts arrive in extremely poor conditions to Mars. This is going to be a very important feature, and we have a whole joint development with space scientists. We had a joint summer school last year with space scientists and nuclear scientists studying together the effects of radiation on long trips. And this is definitely one of the FAIR cores. You see how things spread from space science to the medicine to there is a whole process of continuous technology transfer from basic science over to applications which have an immediate effect on everyday life. Another field which is now developing in some sense also pushed by COVID is that people have difficulties traveling, and therefore we are developing more and more remote control of our instrumentation. We were taking data last year with several detectors of the future CBM experiments, and our colleagues from India were controlling and their components from home.
Oh, lovely. Very fascinating.
So you see that this is constantly developing our ability to handle big science actually from the home laboratories, even without moving. So this is one of the challenges for the future. And in some sense, COVID has given us a shake and a push to go faster in that direction. And we are trying to do it.
Any message for India's Prime Minister Narendra Modi? He has a special affection for science and technology.
It's just a small reminder. There is a laboratory which India owns, which sits in German territory because it is built in parts by different countries, but which India has largely conceived, and where there is a huge scientific community in India which can exploit. It would be a pity not to foster this exploitation from the Indian community and Indian industry that can build on this ownership of this laboratory and just use it as much as possible. It's harvest time, and it is important that the government blesses the scientists and the industries so that they can make optimum use and optimum return for India of the technology developments and the knowledge developments. After all, India knows since hundreds of years that technology does not exist without the knowledge that is behind it. So you want to be present in both. You want to be present in the technology, in the application, and in the brain development. So, and this all, in the end, sits on the fact of young people being given the opportunity to work on this and to develop their talents that then will go in academia, but also in industry. This is a talent factory. We are very proud of this fact. And India owns it. Use it.
Thanks a lot.
Use the most possibilities for your own young people, because it's yours. So why not to make maximum use of it?
Thanks a lot for giving me an insight on the fair facility and telling me how it is a talent factory and how India owns a part of Germany while India
Yes.
is still far away, and how Indian scientists could better utilize that facility, and how you created a universe in the laboratory. But what fascinates me is, and I'm not sure whether you'll be able to do that, is to create more platinum and gold, not
Oh,
just
yeah.
by way of knowledge, but by way of real platinum, real gold. It's in lighter vein, you can understand. But the jewels you find within FAIR, I'm sure, is going to lead to a better understanding of the universe. Thanks a lot for speaking to us, Dr. Paolo, and I hope India continues its love affair with FAIR. Thanks a lot for speaking to us.
Thank you a lot for having me. It's a great pleasure. It's really an enriching partnership, and I very much wish this to
Thank
not
you.
just continue, but further develop.
Thank you very much.
Thank you.